In high-volume manufacturing, a microscopic deviation in a single component can trigger catastrophic system failures. Consider an engine component facility producing piston rings. During a 3-month period, internal quality checks forced the rejection of 250 complete lots every single month. These rejections were driven by rigid parameters. Piston rings seal the combustion chamber and regulate oil consumption, making their exact dimensions a critical factor in meeting strict BS6 emission norms. This diagram shows the required physical tolerance limits for the ring's radial thickness. The manufacturing target is 2.9 millimeters, with a highly constrained acceptable variance of plus 0.15 and minus 0.1 millimeters. Repeatedly breaching these exact dimensional tolerances creates compounding costs. Material is wasted, machine time is squandered, and the entire downstream assembly line is delayed. Unchecked process variation directly erodes both regulatory compliance and the thin margins of high-volume manufacturing. A common misconception in modern engineering is that eliminating complex process variation requires advanced machine learning or multivariate statistical modeling. Dr. Kaoru Ishikawa presented a much more efficient premise that 95% of all quality problems can be isolated and solved using a fixed set of visual exercises. These exercises are the 7 basic tools of quality: the check sheet, Pareto chart, flow chart, cause and effect diagram, scatter diagram, histogram, and control chart. To deploy these tools effectively, engineers utilize the DARE methodology: define, analyze, report, and engage. DARE organizes these 7 distinct charts into a sequential, step-by-step diagnostic funnel. The power of these tools lies in their ability to force cross-functional teams to align on an empirical reality, replacing subjective debate with visible data. The define phase of the investigation begins directly on the factory floor, capturing raw symptom data at the exact location where it is generated. The first tool deployed is the check sheet. This provides a real-time, structured collection method for tallying qualitative or quantitative defect data as the process is actively observed. Tally marks alone are insufficient. To ensure data integrity, the check sheet must capture metadata, documenting exactly who collected the data, what batch was tested, where it occurred, and when. Once the raw check sheet data is compiled, it is evaluated using a process failure mode and effects analysis, or PFMEA. This table illustrates how the PFMEA generates a risk priority number. By multiplying severity, frequency of occurrence, and detectability, engineers weigh each issue's threat level. For piston rings, the radial down-high defect carried the maximum risk priority score of 378. Raw data collection without a risk ranking framework produces operational noise rather than engineering direction. The investigation now shifts into the analyze phase to categorize the mass of defect data collected during production. To process this data, we rely on the work of quality pioneer Joseph Jurin, who popularized the 80-20 rule based on Vilfredo Pareto's economic observations. The core concept of the Pareto principle is efficiency, separating the vital few root causes that drive the majority of issues from the trivial many. This Pareto chart maps occurrence frequency vertically and defect categories horizontally, sorting them from highest on the left to lowest. A cumulative percentage line tracks to 100%. The conclusion is immediate. Over 80% of rejections stem from the radial thickness defect. Applying a Pareto filter prevents organizations from wasting engineering hours on mathematically insignificant problems. Knowing that radial thickness is the primary defect does not reveal the mechanical mechanism causing it. The investigation must transition from what is wrong to why it is happening. The flowchart is the essential tool for this step, visually mapping the exact sequence of the manufacturing process as it actually exists on the floor. The flowchart pinpoints the exact operational stage where the radial thickness is formed. Step 4, the inner diameter boring process. To generate root cause hypotheses for that specific boring process, the team deploys the Ishikawa, or Fishbone diagram. The Fishbone breaks down variables into standard categories: man, method, material, and machine. Teams populate branches with hypotheses, like unspecified sleeve change frequencies or unaligned bearing assemblies. The primary defect occupies the diagram's head, focusing the root cause analysis on the highest impact variable. The Fishbone diagram replaces scattered assumptions with a structured, universally visible map of potential variables. A hypothesis placed on a fishbone diagram remains an assumption until it is proven by hard empirical data. We verify these hypotheses using stratification, the act of sorting raw data into distinct layers based on its source, such as specific machines, operators, or shifts. When data is lumped together from multiple sources, it often masquerades as random, unsolvable noise. This scatterplot visualizes stratification. By separating data, distinct color-coded clusters tied to specific variables emerge from the noise. It acts as the verification tool, placing the controllable variable on the x-axis and the response variable on the y-axis to confirm correlation. Establishing visual correlation is the mandatory final step to prove a mechanical hypothesis before committing capital and downtime to a physical fix. The narrative now enters the report and engage phase, where the physical solutions are implemented and measured against the baseline. To measure the natural variation patterns and frequency distribution of the process, engineers use the histogram. This histogram represents the initial before state of the piston ring batches. The data forms a wide, flat bell curve. Because the curve is so wide, data spills over the upper specification limit, resulting in an unacceptable process capability index of 0.68. The facility implemented action plans, addressing bearing assembly alignments and enforcing strict tool change schedules. Following the fix, the after-state data shows the histogram's bell curve drastically narrowing, centering safely between the limits and achieving a world-class CPK of 2.45. A centered, narrowed histogram is the mathematical proof that a root cause has been successfully eradicated from a system. Physical systems continuously degrade. Tooling wears down, environments shift, and initial fixes naturally drift over time. To maintain the newly stabilized process, we deploy the seventh and final tool, the control chart, standard practice under ASTM E2587 guidelines. The purpose of statistical process control is to differentiate between the normal, expected common cause variation and sudden, assignable special cause anomalies. The control chart plots chronological data between limits, alerting operators to any breaches. The dashboard is now complete. Checksheets capture data, Pareto prioritizes, flowcharts map, fishbones hypothesize, scatterplots verify, histograms prove, and control charts secure the process. When deployed in sequence, these 7 tools form a unified diagnostic engine capable of mastering high-stakes industrial complexity.